Okay, let's look at this Biot-Savart application. In this problem, I have a wire that's kind of with a couple right angles in it, so it's bent basically into three segments. And when we have a situation like this, my advice is usually to break this up into the number of segments and look at those segments independently. It often really simplifies the solution. So for this problem, I'll number these. I'll call this left one segment 1, the 7A segment 2, and then this rightmost segment 3 here. And we'll just handle them one at a time. And I can know that the B field at point P is simply the sum of the B field of each one. So if I look first at segment 1, what I actually am going to do is make a separate diagram for each one of these. And this diagram is my analytical diagram. It doesn't have to be exactly to scale. I want to leave space for making the diagram be meaningful and stuff I need here. So for this first segment, we have, there's the wire. I have current going. In this case, it's upward in this wire, and then my point of interest P, which is up here. And what you might notice right off the bat here is if I have my DS, so that'll be in the direction of current here, my DS. And then if I were to, I'll just switch out the colors and add my R vector here. It goes from the source current, from a differential element, to my point of interest. There's my R. And I can see right away that I have a parallel relationship between R and DS. So that cross product between DS and R is going to equal to 0. I have no normal components at all. So that will be 0, and the B field at P due to segment 1 here is going to be equal to 0. So we're not saying the segment doesn't create any B field. It obviously does, and that would be visualized in concentric circles around the wire segment, but it doesn't have any contribution at point P. So segment 1 is done. Great. Now we move on to segment 2. So let's do segment 2. Segment 2 is going to contribute. Let's make a diagram for segment 2. Again, just a separate diagram for each segment that allows you to focus on the segment you're working on. So if I do that here, I can, so here would be my wire. So here is my 7A wire, and point P, I'll float point P up here. Again, I'm not worrying about putting this to scale or anything. I want to make sure there's space actually in my diagram for the things that I need. And this wire is 7A in length, and I know that the current is going off in toward the right there. And I'm going to go ahead and put a coordinate system on this. So it's another thing is you might want to use a different coordinate system for the different segments. So I'm going to use, I'll put positive y here, positive x to the right, and just to be super clear, what this means is that I'm putting my origin, my coordinate system origin at the left end of the wire there, of this left end of this segment. So then I can do my normal stuff, pop in my ds here. My ds is going to be in the direction of current, and then I can write in my r vector. R always goes again from your current element, from your differential element to your point of interest. So there's my R vector. Okay. Now, the Biot-Savart that we're using, I like to hand you guys the vector form of Biot-Savart because you can handle that. And one of your first moves then is to turn that into magnitude form. So let's do that together here. So notice that now there's no hat over that B. I'm just expressing magnitude. Magnitude of a cross product is the product of the two vectors multiplied by the sine of the angle between them. So the sine of the angle between them is something that needs to be put on your diagram, and I'll do that with the angle phi right there. So then I'm pretty much ready to go ahead and start defining stuff I need to define here. I see that the way I have my x defined, that the quantity x is actually going to go from the origin to where my differential element is, right? So x locates my differential element. So it would be kind of like locating that. X locates my differential element with respect to the coordinate system, which is my choice. And R locates it with respect to the point of interest, which is all about the problem that was presented, right? Okay, so then I can start defining stuff. I can define R here. Just gonna kind of separate this 2 from 1 there. My R for this particular case is going to be the square root of 4a squared plus x squared. There's my R. And then I can also define my sine phi. So that'll be opposite over hypotenuse. So that's 2a over r. All right. And then, of course, my ds, I'm going to define as dx. So this ds equals dx. And it's just a little bit of length along the x-axis. And again, the only time I really would use s when it's appropriate for s is conventionally used for arc length. But if you're going along any other axis, you should rename it there. S is too general to use for like everything, right? And it's weird to have an S axis instead of X and Y. Just that's weird. So don't do that. Okay. So then I guess we're ready to move on with our dB. Let's go ahead and rewrite it. Again, this is just magnitude, right? I can get the direction. We'll do that in a sec from right-hand rule. So this is going to give me dsr dx. Then I've got 2a in the numerator, and then I've got 4a squared plus x squared to the 3/2 power in the denominator. So when I'm writing out my integral for b, I'm just adding up all the db's, right? And so I can pull out all the constant stuff. So that'll be 2a mu naught I over 4 pi. And that leaves me with dx over 4a squared plus x squared 3/2 power in my integral. And for that, I will look at my bounds. And here for my coordinate system choice, I'm just going to go from 0 to 7a. Okay. So yeah, I can integrate that, and that will give me my magnitude for B. Let's pause for just a second though, and we do need to think about direction too. So let's go back up and look at our point P and think about dB and what its direction would be. So if I use right-hand rule and I say ds crossed in with R, that gives me a B that's dB that's out of the page. So I can mark that in there. dB is out of the page there for segment 2. Okay, so that means that when I finish writing my B here, my final result here, and you'd have to do the integration and evaluation. Those steps are in the written solutions. I'm not going to do all those steps out here. I think I end up with 7 mu naught I over 8 root 53 pi a, and that direction is out of the board. So I'm okay when you're in this third dimension for you to use in and out of the board. I actually prefer it to the K notation, K hat. It's fine if you use K hat. You have to define K hat though, if you're going to use K hat. The reason that for right now I'm kind of promoting the use of in and out of the page is it's a little bit more physical. And for many students, this is new, working in this third dimension that's in and out of the page. So keeping it a little less abstract and a little bit more physical can be helpful. So anyway, this is the B field contribution for segment 2. Should be more clear about that. Okay, so now let's look at segment 3. We have one more segment, and that is that 2A segment. And I'm just going to draw that out. So this is segment 3 here. And it's kind of like, again, I'm drawing a little bigger, but it's 2A segment in that direction. And current is upward there. And then point P, let's go back for just a second, look at the diagram here. So point P is 7A off to the left of the top side of that. So we could draw like point P right in here. And this distance between P and the top of the wire there is 7A. And I'm going to use this as my coordinate system when I'm drawing in right now, actually. So I'm going to use positive Y downward here just to keep my real estate positive, and I'm going to use positive X leftward. And again, that's just the fewer negative signs I'm carrying around, the way that I see it is that's fewer mistakes I can make because fewer signs that I could possibly drop. So my preference is usually to stay in positive real estate if I can. So that's informing this choice here. That means my origin is right here. Okay. So it's kind of good form to have all of that labeled on my work because, I mean, if I'm expecting someone else to read this, the coordinate system is entirely my choice. This problem didn't come with the coordinate system. So I know that this length here is 2A, and I know that this distance up here is 7A. That's given in my problem. So now let's go ahead and pop in our ds. I'll put that here. That is going upwards, and I can say there that ds is equal to dy here. I'm moving along the y-axis. And some students will sometimes ask me, well, why can't I just rotate the whole thing or just call that x instead because I prefer to work with x? And I would say, well, that is actually a sign to me that you should do it this way so that you can have some reps working with y, because you shouldn't I think it's best to feel just as comfortable working with x as working with y, and not to have a favorite there, because sometimes you just have to be in 2 dimensions. So I'll draw in my R. It goes from my source current to point of interest. There's my R. And then I'm going to remind us of the Biot-Savart magnitude here. Let's just be reminded of that. Mu naught I over 4 pi. Again, we have ds, magnitude R, multiplied by the sign between them, and that's all over R cubed. Okay, so that just kind of reminds us what we need to be looking at there. And that the angle here, the angle that I care about is the angle between ds and R. And sometimes if someone's not paying attention, they might mark the wrong angle in their diagram. So always remember what it is that you're trying to express a cross product between 2 actual vectors in space. So that would be my phi for this case there. And then for this one, let's stop right now and figure out our dB direction. So you can say ds crossed in with R and do right-hand rule that way, and that will give you your dB as out of the page. So in this particular problem, the segments either don't contribute or they do contribute in exactly the same direction. It's not always that way. Sometimes you have segments that contribute in opposite directions, and so you need to give them opposite signs in the solution. So pay attention to that. My ds, now I'm trying to think what else we have to do here. Let's define our R. So if I define my R here, that's going to be, now notice that we go from the origin down the y-axis, right? So this distance here, let's see, where can I draw that in? This distance here is y. Sorry, that's kind of squished. From the origin to the location of my differential element because that forms the base of the triangle. So I actually care about that. So r is going to be square root of 49a squared plus y squared. So you can write that as quantity 7a squared. I find that sometimes I'll mess that up, or I'll drop a paren or something. So I'll just square it right now, and then I won't worry about that problem. I'll just carry that around with me instead. So there's the r, and then I can also define my sine phi for this problem. Again, that's opposite over hypotenuse, so that'll be 7a over r. And pause at these steps and do them intentionally. This is a silly place to make a mistake in a problem like this. It's just right triangle stuff. So take your time. The reason that in the solutions I always write these out intentionally one at a time is so that I can focus on defining them properly, and just focus on that one thing for just a moment. And it's worth doing to do it right. So now I can write out my expression then for dB. Why don't we do that? Mu naught I over 4 pi. So here I've got my 7a in the numerator, and then my dy all over 49a squared plus y squared, and that will be to the 3/2 power. So that is my dB. Now I know that my b, this is b for segment 3, dB for segment 3, is going to be adding up all of my dBs for segment 3. And I don't have any cancellation here. Each one of these segments, each little differential element as I move through the segment is, they're all going to be contributing in the same way. They're all contributing out of the page field. So I don't have to worry about any kind of cancellation going on here. I'm integrating because each segment is a different distance away from point P. So they're each going to contribute a little bit differently, and thus the need for integration. Okay, so we can set up our integral. I can pull out constant stuff. Mu naught I, the 7a, the 4 pi, and then I can integrate dy, and I'll have 49a squared plus y squared to the 3/2 power in my denominator. And then here I will be integrating from y equals 0 to y equals 2a. All right, so that'll be my integration. I will integrate and evaluate this at those bounds. And once I do that, what I will have here, actually, you know what, is I'm going to write that over here. In vector form, what that looks like is mu naught I over pi a root 53, quantity 7/8 plus 1 over 14. That can be simplified, but I was pretty happy with just letting that be out of the page's direction. Just like that. And even if you do simplify, whatever you do, please do not use a decimal approximation. We don't do that. So this is fine. You know, this is simplified down. What this does is it allows me to see the general behavior of the thing, and that's what I care about seeing. So then for the whole wire, what I know is that the B of point P, right, is going to be B of segment 1 plus B of segment 2 plus B of segment 3. And I know that segment 1 was 0, right? So really I'm summing up segment 2 and segment 3. Oh, I'm sorry, guys. I realized that I messed something up here. I gave you this right here is actually the total. It's not just for segment 3. So if you were really confused there, then I understand why. So let's scratch that for just a second. And B of segment 3, just for segment 3, is mu naught I over 14 root 53 pi a. Okay, out of the page. That'll make a lot more sense. So when I sum segments 2 and segment 3 to find the total b, that's when I get, so this is my final answer, mu naught I over pi a root 53, and now I'll have my 7/8 plus 1/14, and those just came from the different contributing terms. So this is my final answer here for B at point P.